Good afternoon, everyone. So I think we are live now, and how are you? कैसे हैं आप लोग? कैसा चल रहा है आपका दिन? How's everything going? Okay. So in the previous class, what we have discussed about Bernoulli's theorem. Uh, and in the previous class, we have discussed about some equation of continuity. So let's start our discussion over there. Okay. So today what we are going to discuss some of the applications of the Bernoulli's theorem and how to apply Bernoulli's theorem in situations, in questions. So let's see. Okay. So first of all, we will recall our concepts, what we have learned in the previous class. We will recall those concepts. Okay. Okay. So first of all, we have studied about equation of continuity. What is equation of continuity? Equation of continuity was rate of flow. A into V is what? A into V is what? Rate of flow for a tube is constant. Rate of flow for a tube is constant. That was our equation of continuity. Here A is the area of cross section, V is the velocity of the fluid. Clear? And from here we have concluded that velocity is reciprocal to the area of cross section. Velocity is reciprocal to the area of cross section. As you can see, here there is a tube. This is a tube on your screen. Area at the end one is more, so its velocity will be less. So the velocity of the liquid flowing in the tube will be less at end one as compared to end two. This is what equation of continuity is. Now, what is Bernoulli's theorem? Bernoulli's theorem is what? The sum of pressure energy, kinetic energy, and potential energy per unit volume. Per unit volume is constant. This is what Bernoulli's theorem. So you know all the terms, na? Pressure energy, kinetic energy, and potential energy per unit volume. The sum of these three energies is constant. Now, what if I say there is one more important application that is quite often used? What if I say for horizontal tube, for horizontal tube. If I talk about horizontal tube, then in horizontal tube, the height of both the ends is same, like the situation shown in the diagram. This height is h1, this height is h2, but h1 is equals to h2. So this is the case of horizontal tube. In case of horizontal tube, the factor of potential energy vanishes. There is no need to put the potential energy term. So what will happen? P plus half rho v square is a constant. So you can see from this relation, if pressure increases, then velocity decreases, or you can say it in different term, different manner, or in the reverse manner. If velocity increases, then pressure decreases. I'm telling you the crux of this situation, crux of the Bernoulli's theorem and the equation of continuity. So what I'm saying, if velocity increases at a certain portion, then the pressure of the fluid at that portion will decrease. Sorted? Clear? So now you need to answer a question which is on your next screen. I think you will answer that. You will be able to answer that. And you must be actually. The question on your screen is this one. Identify the correct option, and there is another term, options. So there might be more than one correct option. So choose wisely. And the question itself says the tube is horizontal. So this is the tube which is, I'm sorry, which is horizontal. So choose the correct options. I'm waiting for 40 seconds. I think that will be enough. Anyone who wants to answer? Sorry. Okay. So first of all, check the options. Options are in terms of velocity and in terms of pressure. So you need to identify which velocity is more and at which point pressure is more. So again, first talk about velocity. First talk about velocity. As you can see, or you know that velocity is reciprocal to the area from the equation of continuity. So area is more at this end. Area is more at this end. So velocity will be less. So that means V1 is less than V2. This is option number A. So option A is correct. Now, if option A is correct, then option C is definitely wrong. Now come about pressure. What I have told you, in a horizontal tube, if velocity increases, then pressure decreases. If velocity increases, then pressure decreases. So at this point, velocity is more, so pressure will be less. So pressure will be less means P2 is less than P1. P2 is less than P1 is option number B. So these two options are correct. Which two options? Option number A and option number D are correct. Moving further. Now we will discuss some of the applications of some of the uses of, there are a lot of uses of Bernoulli's theorem. Lot of uses, lot of applications you can see. I will discuss few of the applications which involve a numerical portion. I'm not describing each and every application of the Bernoulli. There are a lot of applications like Magnus effect is an application. How the bowler swings the ball, how the bowler spinner turns the ball. All these phenomena involve Bernoulli's theorem. So we will discuss the takeoff of the flight is also involves Bernoulli's theorem. So there are a lot of applications. We are going to discuss a few of them which involves numerical calculation. First application on your screen is Venturi tube. Venturi tube is an important application. What it is? It is actually a tube of a different shape. It is a tube which is used to calculate the rate of flow of the fluid in a tube. For example, there is a pipeline in which liquid is flowing, and you need to calculate the rate of flow of the liquid. Then the Venturi tube is used. They are basically used in refineries, oil refineries, where the I think crude oil or whatever the refined oil is supplied through the pipeline. So it is used to measure the rate of flow of the liquid of the petroleum products. So that's how it is used. Rate of flow of a fluid in a tube. It is used. Now, how it looks like, its construction is like that on your screen, like that. So let me describe it first. Uh, this end, you can see this is, let's suppose, end 1. This is end 2. So end 1 is attached to the pipeline. There is a pipeline in which liquid or fluid is flowing. End 1 is attached to the pipeline. And this end, suppose this is end 3, it is also connected to the pipeline. So somehow there is a gap. You create a gap in the pipeline and fix it. Now, what happens? Fluid enters from this end. Let's suppose that fluid is entering from this end in the tube. You can notice that this portion of the tube is very narrow. This portion of the tube is very narrow. Clear? So I am assuming a few terms. Let's suppose area of this portion is A1. Velocity in this portion is V1 and pressure is P1. And in this same portion, in the second end or second cross section, area is A2, velocity is V2, and pressure is P2. Clear? Now, what happens? You know that velocity will be more at end 2. Why? Because area is less, then velocity will be more. Velocity is more, then pressure will be less. Pressure will be less. Now, what happens? There are two narrow tubes attached at the two ends, at the two cross sections, cross section 1 and cross section 2. There is a pressure difference. At this end, pressure is more, so liquid rises in this tube to a greater height, like up to this height, suppose. And at the cross section 2, pressure is less, so liquid rises up to a smaller height. Let's suppose this height difference is h. This height difference is h. Height difference of what? Height difference between the liquid levels. And this height difference is h. Now, if we can apply Bernoulli's theorem, so from Bernoulli's theorem, you know about Bernoulli's theorem? What it would be? P1 plus half rho V1 square plus rho G H1 plus rho G H1. So what I'm saying, let's consider this tube to be horizontal. Let's consider this tube to be horizontal. If it is horizontal, then there is no effect of height. At both the cross sections, height will be same. So there is no effect of height. So I am not writing the term of height, or I am not writing the term of potential energy here. Is equals to P2 plus half rho V2 square. So I am applying Bernoulli's theorem between end 1 and 2. 1 and 2 के बीच में Bernoulli's theorem apply कर रहा हूं मैं. Now you can see that if I transfer some data, it will become P1 minus P2. P2 is transferred here is equals to this V1 square is transferred there. So it will be half rho V2 square minus V1 square. Clear? Now P1 minus P2 is what? P1 and P2 is the pressure difference. P1 minus P2 is what? Pressure difference. And due to this pressure difference, the level of liquid rises to a different level in both the tubes. So this pressure difference can be measured or can be written as rho gh, can be written as rho gh, and is equals to the half rho V2 square minus V1 square. Now you can cancel out rho from here. So what will become? It will become V2 square minus V1 square is equals to 2GH. Let it be equation number 1. I think it is clear. Now one more thing. Only two things you know. One thing is the Bernoulli's theorem. Second thing, whenever the area of cross section changes, you can always apply equation of continuity for the streamline flow. So I am using equation of continuity from equation of continuity. What you can write, A1 V1 is equals to A2 V2. What are the A1 and A2? A1 and A2 are the cross section areas of the Venturi tube. Cross section areas of the Venturi tube. So these two areas are known to us. We have made the Venturi tube. We know the areas, we know the cross section areas of A1 and A2. So A1 and A2 are known. This height h can be calculated using a scale or whatever the measure using any instrument. This height h can be calculated. So everything is known except V1 and V2. You have two equations. You can easily calculate V1 and V2 from these two equations. I am not going to solve. I am not going to create a formula for you because this is a simple term and this is how you solve the questions. You just don't use the formulas for that. What I am saying, just try to understand. I can easily solve these two equations and put a value in front of you of V1 or of V2. But I am not going to do that, and you should not do that. We will do that in numericals. Clear? So what I'm saying, A1 and A2 are known. H can be measured. So V1 and V2 can be calculated from these two equations. Now what we need to calculate? We need to calculate the rate of flow. Rate of flow, I have told you in the previous class that rate of flow is nothing but the product of A and V. So rate of flow is either A1 V1 or A2 V2. You can use any of these two relations to calculate the rate of flow. I think everything is sorted. Venturi tube. You will identify easily that this is a Venturi tube. So I will give you a simple numerical on based on Venturi tube. Try to solve it out. You will have, I think, 1 minute of time. This is a concept test. What I have done here, first of all, I have applied Bernoulli's theorem and then equation of continuity, created two equations. You need to solve out these two equations only to calculate velocities. If you have calculated velocity, then you can easily calculate the rate of flow. Okay. Have a look at that question. The question says water flows in a horizontal tube as shown. This is a horizontal tube and water is flowing something like that. In this direction, water is flowing. Make sure they have mentioned water is flowing. The pressure of water changes by 600 Newton per meter square between A and B, where the cross section area are 30 and 15 centimeters square. Find the rate of flow of water through the tube. So you need to calculate the rate of flow of water. You have 1 minute of time. Try solving it. Be quick. Okay. Okay, first of all, tell me, at which point pressure will be more? Let's suppose pressure here is P1, velocity here is V1, area here is A1. This is P2, V2, and A2. P2, V2, and A2. So which pressure is more? Which pressure is more, P1 or P2? Just answer this question. Now, from Bernoulli's equation, between A and B, I am applying Bernoulli's theorem between A and B. But it says, and when this is a Venturi tube which is horizontal. So I am not using potential energy term in the Bernoulli's theorem. So what is it? P1 plus half rho V1 square is equals to P2 plus half rho V2 square. This is very simple term. Again, you can transfer the terms. P1 minus P2 is equals to half rho V2 square minus V1 square. This is exactly the same thing that we have done previously. And this P1 minus P2 is the pressure difference. P1 minus P2 is the pressure difference. When we were studying Venturi tube, we have discussed that this pressure difference is is calculated by the rho GH. But here this pressure difference is already given, which is 600 Newton per meter square. 600 Newton per meter square. So I will directly place the value, that is 600 is equals to half rho. Rho is what? Density of liquid, and liquid is what? Liquid is water. So density of water is 1000 kg per meter cube. You know that this is a, that's why I have highlighted the term water, because density of water is known. So don't ask for the density of water to be mentioned here. Now, this is V2 square minus V1 square. You can solve it out and make equation. I think these two zeros will be cancelled out. Okay, so this will be 5, 6 by 5. So the equation is V2 square minus V1 square is equals to 6 by 5. Let it be equation number 1. I think to this point, everything is clear. Now, what I have told you, that use equation of continuity to make second equation. So I am using equation of continuity. So I'm not writing it here that from equation of continuity, I'm just directly using it. That is A1 V1 is equals to A2 V2. Most of you are late in the class. Uh, I don't know why, but you have missed certain things. You have missed a complete topic of Venturi meter or Venturi tube. You have completely missed it. You have missed the recall test. You missed a lot of things today. A1 V1 is equals to A2 V2. This is not a formality that you are joining the class and just leaving the class. You need to learn few things. Na? So now I am putting the values of A1 and A2 here. A1 is what? This is given as 30 centimeter square. A2 is 15 centimeter square. Now I am not going to convert the unit because both these sides, they are same unit. So they will cancel out. So it will be 30 V1 is equals to 15 V2. I will solve it out. So V2 is equals to 2V1. This is our equation number second. So if I put the value of V2 in equation number first, I will get V1. I am putting from equation number first. If I put V2 as 2V1, so it will become 2V1 square, that is 4V1 square. I am using the, I am skipping few steps here. V1 square is equals to 6 by 5. So I will say 3V1 square is equals to 6 by 5. So V1 is what? This will be 2 root of 2 by 5 meter per second. This is what velocity at the end A. They are asking about rate of flow. They are asking about rate of flow. So rate of flow is what? A1 into V1. A1 is what? 30 centimeter square. 30 into 10 raised to the power minus 4. This is A1. Into V1 is what? Root 2 by 5. This is our answer. That is meter cube per second. This is the rate of flow. The question may look dangerous, may look lengthy, but it's not. It's a simple question, doable question in the exam. If it comes in the exam, you can easily do that. You just need to apply Bernoulli's theorem and then equation of continuity. You can easily solve it. Rest is your calculation, how quickly you can calculate it. Okay. Have a look at that. After that, we will move further. This is the one of the applications. What we have studied till now in the today's class, we have studied these things. Okay. From here, we have recalled equation of continuity and Bernoulli's theorem. There is a recall test. There was use of Bernoulli's theorem, that is Venturi tube. Okay. So now there is a concept test. Now we will move further. Speed of efflux. This is again a very important topic from which the questions may come most of the times. What is it? This is again a use of Bernoulli's theorem. What it is, just try to listen it out. Okay. Listen. Let's suppose this is a container. This is a container in which some liquid is filled up to a height h. Some liquid is filled up to a height h. Clear? And a small hole is made on the side walls of the container. This small hole is sometimes known as orifice. What it is called as? Orifice. Sometimes you can call it a hole, whatever it is, but when the hole is very small, it's sometimes called as orifice. Okay. So a small orifice is made at a depth small h from the surface of the liquid. Mark my word, this height small h is taken from the top surface of the liquid. Clear? I think it is clear now. Now, what you need to do, you need to calculate the velocity of the fluid coming out of the orifice. That means you need to calculate this velocity. Which velocity? This velocity. You need to calculate this velocity. The velocity with which liquid is coming out of the orifice. Clear? Now, let me assume one more thing here. The one thing that I am assuming here is, if just notice one thing, the liquid will come out of this orifice. So the liquid level will decrease in the tank or whatever it is, but the decrease or the fall in the level will be very slow. So the velocity of the top surface is very low as compared to the velocity of the fluid coming out of this orifice. So we can ignore the velocity of the surface. I'm repeating my words again. In this whole calculation, we are assuming, or we can take, we can consider that the size of the tank is very large as compared to the size of the orifice, size of the hole. So the level of decrease or the rate of decrease, rate of fall of the surface is very small. So I am ignoring its velocity. Okay. So let's consider a tube. Let's consider a tube of flow from the top of the surface to the orifice. This is a tube of flow. This is a tube of flow. And now I am going to apply Bernoulli's theorem. Let's suppose this is end A, this is end A, and this is end B. Clear? So I am going to apply Bernoulli's theorem between ends A and B. Now, let me tell you one more thing, that the pressure at this surface is open to the atmospheric pressure. So pressure at this surface is P naught. And at this end, if you notice at this end, the pressure is also atmospheric. Pressure is also atmospheric. So I will apply P naught plus half rho velocity at A square plus rho G H is equals to, pressure is again P naught plus half rho V square. Let's assume the velocity is V plus ka rho G, and height of the orifice from the ground is, this total height is H, this height is small h, so this will be H minus H. This will be H minus H. H minus H. Now again what I'm saying, that velocity A, VA means velocity of the liquid surface going down. And this velocity we have assumed to be negligible. So this whole term will be zero. This P naught will be cancelled by the P naught. So what will remain? Rho GH is equals to half rho V square plus, I will open this bracket, rho GH minus rho GH. Again, you can see that this rho GH and this rho GH will be cancelled out. What will remain? Half rho V square is equals to rho GH. You can again see that rho will be cancelled. So V is equals to, this 2 will go there, 2GH. Two GH under root. This is what the velocity of liquid coming out of the container, coming out of the orifice. Now, this velocity root 2gh is very much familiar. You are familiar with this term root 2gh. This is a famous term used in the kinematics. Just remember, when you use this term root 2gh, first thing, this velocity of liquid coming out of the orifice is known as velocity of efflux. How much this velocity is? V equals to root 2gh, where h is what? H is the height of the hole or depth of the hole from the top surface of the liquid. Just don't get confused. There are so much H. There is a capital H, there is a small h, there is H minus H. So what you need to remember, the H in this formula, what is H? H is the depth of the orifice from the top surface of the liquid. I think it is clear now. Remember this formula. Now I am moving further. I will explain this related to the kinematics. Now there is a Torricelli theorem. Nothing to worry. Nothing to worry about the term. Nothing to worry about the name of the theorem, Torricelli's law. So let me describe one thing for you. Let's suppose. Let's suppose there is a ball. Clear? And this is our ground. And this height is h. Clear? And this ball is being dropped. This ball is being dropped. Can you tell me the velocity of the ball when it reaches the ground? Can you tell me the velocity of the ball when it reaches the ground? You will say yes. You will apply, or you can apply v square is equals to u square plus 2gh. U square is 0 because it is dropped. So v is equals to root 2gh. This is the same formula that we have derived here. That velocity of the liquid, velocity of efflux, v is equals to root 2gh. We have derived it. Now, what Torricelli's law say that? It says that velocity of efflux is the same as the velocity of a body gained by it when it falls freely by the same height, small h. I have mentioned this on your screen. You can read it out. I have told you. Just read it out. We have few minutes left. Just read it out. I think it is clear. V is equals to root 2gh. Just remember this formula. V is equals to root 2gh. Now moving further. This is Torricelli's law. Nothing else. Moving further. Now, the second question is, what will be the range? What will be the range of the liquid? What we have used, this height is as h, this height is small h, this is h minus h. And this velocity was v, and v was root 2gh. Clear? Now we need to find the range of this liquid. How far will it fall? So this is the question of projectile motion, basically simple question of projectile. For that, first we need to calculate the time in which it will reach the ground. After that, we will calculate the range. So let's suppose this is our origin. You can choose origin anywhere. You know how to apply the projectile motion. So in y direction, I'm applying the second equation of kinematics. What is the second equation of kinematics? Y minus y naught is equals to ut minus half gt square. You know the equation, na? Y displacement is equals to ut minus half gt square. Y minus y naught is what? Displacement. Final position minus initial position. I will place the values. I don't know how you apply the kinematic equations. The final position is 0 minus h minus h naught. This is the displacement is equals to the velocity of the liquid initially is in the horizontal direction. So there is no component in the vertical direction. So this term is again 0 minus half gt square. Minus and minus will get cancelled out. T square is equals to 2 h minus h divided by g. So T is equals to 2 h minus h divided by g under root. This is what time to reach the ground. This is what time taken by the liquid to reach the ground. Now I will apply the same equation in the horizontal direction. In horizontal direction, what will be the equation? X minus x naught. This is what displacement is equals to ut, and acceleration in the x direction is 0. You know the projectile acceleration in the x direction is 0. So I'm not writing it. So what is x minus x naught? That is the range. The displacement in the horizontal direction is what? R is equals to velocity in the horizontal direction is what? Root 2gh. Root 2gh into t is what? Under root 2 h minus h divided by g. So you can cancel here. G can be cancelled out. So R will be what? You can see root 2 is 2 under root small h h minus h. This is the range of the liquid. Okay. Ask yourself, what's the problem? I think you might face some problem in writing the displacement here. If you are facing the same condition, just go what you have learned, how you have learned. Otherwise, you can ask me personally, you can ask me in the chat box. I will describe you how I am writing this y minus y naught and x minus x naught. These are the one thing that I can tell you here. Y is the final position, y naught is the initial position. X is the final position, x naught is the initial position. That's how displacement is written, final position minus initial position. And all the displacement, all the positions are taken from the origin. And I have considered origin at this point. I have considered origin at this point. So range is on your screen. I think it is clear to you. Okay. So one more thing that can be learned from here is when this range will be maximum. When this range will be maximum. First of all, you need to remember this formula of range. I think each and every term should be clear. H is the capital H is the total height. Small h is the height of the or the depth of the orifice from the top of the surface. I think these things are clear. Now, one thing is maximum range. There are two questions. What is the value of maximum range? And second thing is one thing that you can notice here. If this orifice is made at different places, this range will vary. This range will vary. So first thing that we need to identify that at which depth the range will be maximum. Are you getting my point? The point is, if you can try it at home, that if you have made several holes here, then at which point or at which depth from the surface, the range of the liquid will be maximum. So first of all, we will identify that depth at which the range is maximum. Clear? So we will do that in the next class because time is up for today's class. Next class is going to be scheduled, I think. So I am just ending the session here. In the next class, we will discuss about surface tension and some terms related to that. Till then, goodbye. And please try to come earlier in the class so that you don't miss, you just don't afford to miss, I think, a portion of the session. Till then, goodbye. Enjoy your day. Watch the score, watch the cricket, play some games, and then